The time has finally arrived to return my efforts to resurrecting this IBM PS2 Server 95 series machine. As you might know from one of my previous videos, the hard drive in this machine that was used to boot it failed, and I finally acquired some replacements. So tonight, after getting filthy dirty cleaning the refrigerator just now, I'm going to do one more video for the night, try to get this thing up and running. Now, as with any other IBM PS2, the place to start when it comes to getting one up and running again, if it wasn't delivered to you in working condition, is to acquire the reference and, for later models, diagnostic diskettes, as they are your way into the system setup utilities. They are also the way to prepare a new hard drive for use by low-level formatting it if the drive is for some reason not blank. Now, low-level formatting is kind of a confusing term in this day and age of intelligent hard drives. The earliest PS2s did have hard drives that could truly be low-level formatted. The newer ones, with drives that have their own internal defect management and things like that, can't be. But in that case, the system programs, the reference and diagnostic diskettes that we're going to make here, using two blank 3.5-inch floppy diskettes, will take care of examining the disk media and preparing it for use within the system. So let's switch over to the command prompt here, and let's get to formatting some floppy diskettes and writing the disk images to them. Now, writing disk images is not terribly difficult, and if you need these programs for your own PS2, I'll post a link in the description showing how you can get them. Now, the disk to go ahead and write first is actually the reference disk. So let's go ahead and use the raw write command to go ahead and write that to a freshly formatted floppy diskette, which you can see the system is doing up there. Here's the diagnostics disk ready to be written. Now, in the case of these particular systems with the processor complex, you need the right reference disk for your processor complex, while the diagnostics are common to all four, or unofficially 5, I guess, processor complexes that are out there. Officially, the processor complex cards only go from 486s of various types to Pentiums, but there was also a special bid 386 complex out there. They're very rare, and systems that survive with them still working today are even rarer, but I have an example of the complex, less the system unit. Now, those who are really paying attention here will have undoubtedly noticed that I'm not using the official IBM PCCBBS diskette extractors. That's because they're sometimes a little bit fidgety. You can go ahead and download them. The PCCBBS has been mirrored in multiple places online. But if you have a 64-bit computer running a 64-bit operating system, such as a 64-bit version of Windows, you may not be able to run the DOS mode extractors to run them, to extract them to disks. Oh, let's see here. So that's the reference and diagnostic disks created. Go ahead and roll over here and get to installing the new hard drives. Probably better turn that stereo down too. I'm probably courting a visit from the music mafia. It's not terribly hard to install a hard drive in one of these machines. Let's see here. Just turn this thing around to where it can be worked with as I push my hard drive back to where I can't actually get it. Oh, there we go. Better not set that on the floppy disks I just made. It's got some fairly strong magnets in it. After you take the front cover of the unit off, which I talked about in my last video, most everything you're going to do is toolless. So once the front panel is off, you have to remove the hard drives. And removing the hard drives isn't too hard, but there are definitely some things to be aware of while you're in here. First and foremost, if you have a SCSI cable running along particularly close to the power supply, as I do right here, watch out for the so-called guillotine, because these little wires, they can get snarled up as that thing is swinging in or out, and they can get broken. You need to disconnect the power cables going to every drive in the system. You'll notice these unplug at the power supply end. They were modular connectors. Oh, something just broke over there. That was fun. And then you need to make sure that the power cord is unplugged, because if the power cord is not unplugged, you won't be able to pivot the power supply out of the system. If all that stuff checks out, you're ready to undo the power supply and flip it down out of place. Now, a word to the wise, do not tighten this connector any more than just this connector. Do not tighten this thumb wheel any tighter than finger tight, because if you do, what will end up happening, pivot the power supply out here for a closer look, there's a little E-clip that holds this into the power supply body. And inside there, inside the power supply itself, is a spring that keeps spring tension against this lever to help it come free from the mating surface near the motherboard. If you twist that thing down, it's well documented that you'll deform this E-clip. It'll go ping, and you'll be left with a spring floating around loose in the power supply waiting to cause problems, and you'll have a handle in your hand. So fixing that requires a set of security bits to get into the power supply. Now the power supply's out, I can work on freeing the drive, which is back down in here. Go ahead and kick up the light a little bit, and you can see how the SCSI cable is connected to the various drives in the system. In the course of replacing the drives in this computer, I'm going to go ahead and simplify things down to just the one hard drive for right now. I'll add the working hard drives back again later. Now, if you had a need to remove the power supply from the system at this point, you'd need to do a couple of things. You need to undo this ground braid if your system is so equipped. You would also need to undo this metal flap here, which, depending on how you undo the ground braid, you can do in one shot, and then the power supply simply slides forward off of these pins. Here's all the power and data cabling for the hard drives disconnected. You can see these power cables are completely loose to wander around inside the system, so make sure you don't lose them. And when you're putting your new hard drives back in, don't force this cable, because you could rip or tear these delicate little multicolored bundles of wire. You could also bend a pin in this male connector here. Go ahead and flip the power supply back up here. With all the cabling, power, and data removed, these drives will just slide right out of the system, just like so. This is the boot drive, and it was bad. These other two DFHS drives aren't too great, so I think they're going to be set aside as well. Some of them fit much more snugly than others. Someone had asked me if I would send them these drives, and to be quite honest, these aren't that great of a hard drive to start with. They were a decent design when they were new. This is actually a DCHS. I thought this was a DFHS, but I guess not. Anyway, these were not the greatest design when they were new, and many of them found use in servers back when they were new, so they ran around the clock for years and years on end, which wasn't good for them. And now they have some pretty serious stiction problems. You can see the date on these, 20 January 98. This one over here, I don't know how old it is. Oh, 04/05/95. I don't know if that's actually a date, but it probably is. So these drives have been on the road for many, many years, and I just don't know what I'm going to do with them. I'm certainly not going to just throw the ones that work away, but I don't know that I'm in a hurry to part with them either. This one's dated 09 July 97 and was probably replaced under warranty or something, because it says serviceable used part. It's something you hear thrown around in the used car business a lot. Now, to get these drives out of their little cages is just a matter of 4 screws, and then they're free. Now, this drive up here is a keeper. This is the newest of the bunch. This says compact on it. I thought this was a 15,000 RPM drive, but I guess not. 18.2 gigabytes, 10,000 RPM, wide Ultra 3 SCSI, which will never be used to full capability in this system, and in fact, my SCA adapter on this drive to take it down to the fast wide SCSI architecture has gone missing. I don't know if it's stuck on the end of a cable in there. I didn't see it. Maybe I borrowed it to do something else, like get the PC Server 500 up and running, in which case it can definitely come back here. Interesting thing is that the screws holding this drive in have backed off, so I probably need to look at fixing that. I thought this was a Fujitsu drive. I have a pair of Fujitsu 15,000 RPM drives around here someplace. I don't know where they went though, so I'll go ahead and pop one of these old drives out of their little carrier and go about taking the new drive and putting it into place. One particular feature that sets SCSI drives apart from the rest is their onboard intelligence. Now, by the time this hard drive was released to the market, IDE drives typically had their own onboard microprocessor as well. However, it was typically just called into service to perform the housekeeping functions of the drive. In the case of a SCSI drive, this microprocessor actually performs not only the housekeeping tasks, but also the drive's communication tasks over the SCSI bus. And you can see here, this drive has an AMD 8186 microprocessor clocked at 20 megahertz. There's also a memory chip back here that is used as a drive buffer, cache, and probably scratchpad memory for the 186 microcontroller. Modern day hard drives have even more processing power on board. In fact, I took the logic board off of a Western Digital parallel ATA drive and I saw a Marvell processor of some kind that was marked as having a 400 megahertz clock speed rating. Now, the old hard drive has been taken out of the mounting hardware and the new hard drive has been put in. You can see that even though this hard drive is from roughly the same time frame, its logic board is greatly simplified, and the functions have been combined from a number of discrete chips into a couple of application-specific circuits. Back here's the power connector and the SCSI wide 68-pin connector. Now down here is a jumper block. For those of you who are familiar with IDE and serial ATA, most of these options are going to seem rather unfamiliar to you. The first thing that really sets SCSI drives apart from all the rest, and SCSI being SCSI for Small Computer System Interface, in case you were wondering about the underlying acronym or how many letters it actually has in it, SCSI has the concept where each device on a SCSI bus has an address all its own. For example, the host adapter has its own address, typically number 7 in some systems. Now, IBM systems differed a little from everybody else's, so some of this stuff that I'm talking about will seem different to those of you who have used SCSI in some other operating environment. But IBM actually is said to have followed the standards for SCSI disk numbering and device ID numbering correctly, as opposed to what other manufacturers of SCSI hardware did. The address is set, in this case, using 4 jumpers total. Now, a SCSI narrow device will only have 3 of these jumpers. They represent ID bits 0, 1, 2, and 3. And those can be added to get the ID that you want. Here, I have the ID bits, let's see here, I have ID bit 2 and 1 set, which should give me an ID of 6. We'll see when I get it put together if I'm remembering that correctly. The jumper over here, jumper number 5, is used to determine when the drive spins up. If you had a server full of drives or some other environment where there were a lot of hard drives in use at one time, you wouldn't want them all to spin up at the same time because doing so could overload your power supply, even a power supply like this one that seems like it would be a bottomless well of current. So without this jumper in place, the drive waits to receive a spin-up command from the SCSI host adapter. There are some serial ATA drives that support this as well. Over here is termination. Termination is another concept that's fairly unique to SCSI, as IDE and serial ATA drives take care of it automatically and don't require the end user to do anything. Termination is basically the provision for a resistor network to stop electrical signals bouncing off the end of the bus. To use a phrase that's very layman terms friendly, that's basically what happens. And a SCSI bus needs to be terminated at each end of the bus, each electrical end of the bus, which in some cases might be different from the physical or readily apparent ends of the bus. So with this drive, at least in theory, set up correctly, I'm going to go ahead and slide it into the system here. Again, you can see the only tool I've really had to touch is a screwdriver to take the drive out of its mounting cage. IBM did a pretty good job with these. So I'll get the old hard drive out of here, and then I'll tilt the power supply back out and hook up the power and data cabling to the drive once again. There, the power and data connections have been remade. And as for the third set of power connectors, since I'm not using them at the moment, I just set them in here. Now, in a proper configuration, there would be a set of tray blanks here to prevent too much of the power supply fan's air draw from coming out of the front panel. But let's go ahead, put the front panel on this thing here, if I can do this one-handed. I think maybe I can. Yep, there we go. Front panel's in place. Now, if I was really feeling smug, I put the side panel on, although I'm sure that doing so would effectively seal my fate and guarantee that I had something set improperly. So I'll plug this machine in, start it up, and see how it goes, and that's where I'll need the reference and diagnostic discs. I went ahead and changed my mind about having the side panel on because this machine is running a much faster processor than stock, and the voltage regulator hasn't yet received an improved heatsink, so rather than take my chances, let's go see if this thing starts up. There you just heard the automatic fan control in the power supply kick the electric cooling fan up. I heard that hard drive spin up and initialize, and the machine is booting, so let's do a little bit of hoping. Oh yeah, we've got power on self-test error codes galore. Device configuration was changed. Hopefully the disk drive's still good and it'll boot up. It reports the wrong clock speed on the display, so just ignore that. It's really clocked at 180 megahertz right now. Luckily, as previously mentioned in one of the first videos I ever uploaded, if not the first video I ever uploaded, you can take this display under software control and make it say almost anything you want. And so here the system is asking to go through automatic configuration. It tells us of the SCSI disk errors that it's got. And so we'll go in here and set configuration. She's probably going to complain about the token ring streamer and not having an adapter definition file for it, because every adapter installed in the expansion slots of this machine has to have a textual file on the reference disk explaining how the machine is to configure it. This is plug and play long before there ever really was plug and play. Yep, I knew it. I'll have to add that later. I don't have it handy right now. Now we can view the SCSI device configuration and set up the newly added hard drive and remove all the old ones. Verify that the newly added hard drive is also on the right ID. And as you can see here from the entries that say question, 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 there are a number of devices that are no longer here, so we're going to take them out of the system's configuration map. Whoops, we want that one to stay. And then when I'm done, I'll go ahead and save the settings here. But it looks like I got the new hard drive set up properly, because there it is at ID 6, 4.3 gigabytes. There's a greatly cleaned up version with all the non-existent devices removed. You can see the host adapter at ID 7, the new hard drive at ID 6, and the CD-ROM drive at ID 2. So now this machine is almost ready to have an operating system reloaded on it. There's just one more thing to do. Actually, just as kind of a fun thing to do, I'm going to go ahead and see if there's any bootable operating system on this hard drive that I chose to install. It would appear that to a certain extent there is nothing left on this hard drive, at least nothing bootable left. Oh well. Now with the system up and running and the new hard drive installed, it's time for the exciting phase known as low-level formatting the new hard drive. Now low-level formatting is one of these terms that you have to be kind of careful with, because it means different things depending on the type of computer hardware that you are currently dealing with. In the early days of hard drives that were available to and interesting for the average computer user, low-level formatting meant exactly what it sounded like. The first function of a low-level format back in those days was to lay down a set of so-called servo tracks that the drive's tracking system and head stack could use to locate a given position on the drive. It was also used as a means of finding the defective spots on the drive. You see, every hard drive ever made has certain defective spots, though I suppose that with any other mass-manufactured object, a truly perfect drive does come along, statistically speaking, every now and again. When you bought a hard drive back in the old days, on the top cover was printed a so-called defect map of the problematic areas that were found at the time of the drive's manufacture. Over time, and as the drive aged, or when you put it into service for the first time, you might find additional defects in the drive's surfaces while you were low-level formatting it. And you would record those values into a software program during the low-level formatting process. Now, today's hard drives have done away with pretty much all of that sort of thing. Today's hard drives cannot truly be low-level formatted any longer because the servo and tracking information is laid down at the factory. And in fact, if anything would destroy it at a later time, that drive is basically a paperweight because the end user has no way to lay that information back down on the drive and make it usable once again. Modern hard drives also hide their defects using intelligent reallocation schemes. Any modern hard drive is carrying a set of spare sectors that may be used to replace sectors that are bad at the time of manufacture, or sectors that eventually become bad later on in the drive's life. So with these newer drives, a low-level format means something a little different. And where a modern hard drive has automatic defect management, although it may require a little prodding and encouragement with a suitable disk utility, such as Gibson Research Corporation's SpinRite, bad sectors are supposed to be mapped out automatically, the data recovered from them if at all possible, and a new good spare placed in place of the old sector that went bad. This drive, this SCSI drive, is something of a transitional period between the time when you had to enter all the defects manually and a time when the drive automatically figures out where the bad spots are. The low-level formatting in this case actually does a media test over the drive, typically does some kind of pattern writing, although it's up to whoever programmed the microcode in the drive just how serious and thorough they want to get with this sort of thing. And then, in addition to storing information about the defects which already exist, it looks for more of them and it automatically places them in the drive's so-called grown defect list. So let's go ahead and do this. The way to do this on an IBM PS2, keeping in mind, of course, that this will destroy any and all data on the hard drive. So really, don't do this on any computer system unless you fully understand the ramifications of doing so. The way you do this on a PS2, you need to boot from the reference disk first. You need to make sure that you did not start up from your system's reference or convenience partition if it has one. So make sure that you start up from the actual reference disk. If you try to do a low-level format of your system's startup drive, it will refuse to do so if you are actually running the system programs, the reference and diagnostic disks, from that hard drive. So you'll be at the reference disk main menu, and what you will do is you will hit Control-A on your keyboard to enter Advanced Diagnostics. Now, even though the highlight moved down to where it says Test the Computer, you want to press Control-A because you get more options, because that tells the system that you want to run Advanced Diagnostics as opposed to just the normal user-accessible diagnostics. And like it says, remove the reference diskette, insert the diagnostic diskette, then press enter. So we'll go ahead and do that here. There's the diagnostics diskette, which is hopefully good, and the system will go ahead and start from that. And you get two options here. You can run system checkout, or you can format the hard disk. Now, for those of you thinking that you might be able to just start the diagnostic diskette directly and skip over the reference diskette, you cannot do that. You will get an error message if you try to boot the diagnostics diskette directly. So do the reference disk, do Control-A, and then switch over to the diagnostics disk. We're going to choose the Format the Hard Disk option, and the system will think about it for a while before it returns a possibility of the hard drives that may be formatted. If you have a system with multiple hard drives in it, it's vitally important to know which one you want. In this case, we only have one at ID 6, 4.3 gigabytes in size, so we'll go ahead and select it. The data integrity test, option number 1 above, is non-destructive. The option number 2, which is the option we'll take, is most assuredly destructive to data. So we'll go in there, take that option. I always store the grown defect list. It's unlikely that a bad area on a drive is somehow magically going to get better. But hey, it's your data. You do what you like. It explains what SCSI adapter you're working with, what the physical unit or SCSI ID number is, the logical unit number, and upon which expansion bus, although no microchannel machine has any more than the one expansion bus. Then you get the question that you'd expect to get down here. Are you sure you want to continue? Now watch this, because it's worded trickily, so you can't just hit yes, yes, yes. There are multiple confirmations here. The first one is yes. The second one says, do you want to stop now? And if you choose yes, you would stop. So we'll choose no. This is your last chance to stop. They're not joking. So think very carefully about doing this before you commit to it, because once you've committed to it, it can't be stopped. You may even consider putting the system on a backup power supply during this time, because to have a SCSI drive lose power while it's being low-level formatted can actually end up bricking it. I'll go ahead and choose yes, and at that point you'll see this dialog on the screen. Now, depending upon your hard drive and whoever programmed the firmware on it, you may or may not see the percentage complete indicator. This process will probably take anywhere from a half an hour to several hours, during which time the media surface on the drive will be examined to a varying degree of aggressiveness depending upon how the drive's onboard microcontroller has been programmed. But when the low-level format concludes, it's ready for an operating system to be installed on this computer, and I will talk about that in a future video. Before I wrap this video up, I'll talk about what happens after the low-level format has concluded, at least in terms of putting the system programs back on the hard drive. Now, for a system like this, which has a flash BIOS, you don't need to have the system programs on the hard drive, but it can be convenient when you change the configuration of the computer's hardware to not have to go and find your reference disk and your diagnostics disk to get the system configured. Other systems that actually load their BIOS from the hard drive, such as the PS2 Model 56, have to have the system programs put back in place, or the system will not work properly at all. You can see that in the time that I've been speaking, the drive is now 12% low-level formatted, so this probably won't take all that long in the case of this particular drive. The low-level formatting operation has now completed. It took this drive about a half an hour to do it, so that wasn't too bad at all. If the operation had not concluded successfully, there would be a red-colored dialog box displayed at the bottom of the screen. With this done, the diagnostic program can now be exited, and in fact it gives you another confirmation that the hard drive format did indeed complete. So we can choose enter to get out of that, and then we get the message saying you are leaving the testing program. In this case, we will be starting the system from a diskette, the reference diskette, in preparation for recreating, in this case, the reference partition and reinstalling the system programs to it for convenience's sake. With the reference diskette having been started over again, we'll take option number 2, backup and restore system programs, to start putting the reference partition back in place. Now, in order to do this, you'll need to have both the reference and diagnostic diskettes handy. Take option 3, and the system says make sure that you have the reference and diagnostic diskette or backup copies before you continue with this procedure. It'll go ahead and create the system partition, and then it'll actually reboot the computer into a special operating mode, at which time it restores the files on the reference or system partition. And that's pretty much everything there is to installing a new SCSI hard drive, low-level formatting it, and reloading the system programs on an IBM PS2 Server 95A series system. So thank you for watching, and definitely feel free to leave a comment if you have one.